So, hi everyone, and welcome to my channel. Today we're going to try to implement something quite interesting. We're going to try to build a generic parser. So basically, you provide the grammar of a language, the language that you want in a configuration file, and then the parser will dynamically read the configuration file and create some sort of a set of rules to be able to parse some text that should respect uh, the language that you provided in the configuration file. So basically, after having instantiated the parser with onward the configuration file, you can provide to the parser a text. It will first check if the text well respects the syntax that you provided, and if yes, it will return some sort of a data structure allowing you to iterate through the tokens. It's basically this. Uh, so yeah, let's dive into the implementation. I think it will be quite interesting. I heard about something named Yak. It does, I think, basically the same, but it's for C. We're gonna do it in Rust. So let's create a new Rust project. gparser, I don't know. Okay, so first thing first, we want to describe a grammar in a configuration file. The grammar will be like this the very first inputs for the generic parser. So, and we want to grammar.conf file, and we have to define a syntax to define grammar. That's basically this. So first, the grammar has alphabets. So alphabets are just a set of ASCII characters. For example, we can describe the alphabets for digits. So it could be something like this, probably. Okay. And so digits will allow the parser to build probably numbers. And then you will be able to describe the rules to build a number onward this one, but later. Um, so yeah, basically an alphabet is just a very primitive set of ASCII character. You can define as much as alphabet as you want. For instance, you can define letters. Uh, Probably we're gonna put a S here. No. Uh, you can define letters. So it's gonna be I don't know. Yeah, all the letter. I'm gonna this one is a bit longer, so I'm not gonna write it fully write it. But that's the idea. And for instance, imagine you want to create a language where the numbers can be represented only with 0 and 1, like only binary numbers are supported by the language. You can just simply do this. Oops, simply do this because you don't want to consider 2, 3, 4, 5, 6, 7, and 9 as digits for to build numbers. And that's the opposite. Imagine you want to support more digits, you can add this. I don't know. That's the idea. That's basically what alphabet is. It's very alphabet is very simple. And then comes tokens. So here you can define tokens. So to define the tokens, you have to write the regular expression. Uh, it's not really a regular expression, the set of rules to build the tokens. So for instance, if we want to build a number, I don't know, idents, we should provide identifier, we should provide a letter right here. So no, 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 I'm not going to fully write this, but here, let's imagine all the letters are here. And imagine you want to define identifier. You can, for instance, do this. So what is an ident? An ident is probably a letter followed by another ident. Okay, and probably eventually. So this thing is recursive. So, like we are reading the first letter, then we are reading another ident. And one day we're gonna find EOW, the end of word. It's basically this, like it's like the break condition. So that's basically how you are gonna define rules to build a token. So this one doesn't work. For example, the anti-identifier is accepted and it should not. So if we would like to rebuild an ident rules for ident, we should do something like this. I suppose ident2, and ident2 is probably digits or with the plus operator ident letter followed by I don't too. And eventually we can have the end of word. That's basically it. Like you're providing the rules right here. And you can define as much as rules as you want and as much as token as you want, as long as they only contain valid things. Okay, in today's video, because I think I'm gonna code the entire project in multiple videos, because it's probably gonna be quite long, we're gonna try to parse the configuration files and output a data structure that represents the rules of the grammar, I think. So we will have to first parse this thing and then parse this thing. Uh, this thing will be a bit hard to parse because we need to first evaluate this expression uh, and then output something that represents the rules and allowing us to parse the text furthermore. So yeah, it will not be that easy. So I think it will be the subject of the entire video of today, the simple parsing of this kind of configuration file. Okay, so let's do it. Um, something like let's just um, a pass. I want to provide a pass. So here I can just say grammar.conf and then we have to read grammar.conf. So let's do this. I'm gonna anyhow, I think. I don't want to deal with complex error handling. I'm gonna add it here. Use anyhow. I want result, context, probably bail and surely unsure, I suppose. I'm gonna return nothing, just a result. Okay. And so the path will be std and args and nth one dot context. Please provide a path. Then I want to read the file, to open the file, sorry. So stdfs file open a path context invalid path. Okay. Oops. This thing gonna be mutable, and I'm gonna read the content of the file. So it's gonna be a string. And it's gonna be f.read to string context. Okay. And here we can print it. So that's how we read the file, the content of the file in Rust. It's kinda simple. And so I can just run, and it failed because I have to include stdio read, I suppose. And I have to put content as mutable, of course. Okay, nice. And here I have to handle the error. So it's gonna be failed to read file contents. To read the contents of the file. Okay. Now let's read the contents line by line for line in contents dot lines. I'm just gonna read the lines, and I'm gonna probably like trim the line before dealing with it. So it's gonna be line dot line dot trim, I suppose, and I'm only gonna retain I'm only gonna return the line that are not empty. Line dot is empty. It should never be empty. And so here we have the line. Okay. So yes. I'm trimming because I don't want to deal with like extra spaces. Like I want to remove these spaces and probably these spaces too. So it's basically in here. I think it works. It removes the spaces. Okay, nice. Now the next thing I want to know is I am reading a line that define alphabets, or am I reading a line that define tokens? So I have to include something like a state. So let's introduce like an enumeration. It's gonna be enum states, and there are gonna be two states. The first one gonna be alphabets, and the second one would be tokens. That's basically it. And I want to have let's introduce a structure, I suppose, like a configuration parser. The struct has a state, and we can implement it, I suppose. Conf parser and create a constructor. So new, gonna return self, and it's gonna be like this. And the first state, now I don't want the first state to be alphabets because I want this to be valid. Like if you want, you can define token first, and then we have to handle like the fact that letter is defined later. Letter is defined later. It's basically this. So I can't say yeah, the first state is anyway alphabets. So I have to introduce like a default state. So like probably nothing or before, I don't know, but nothing is good. So nothing is basically just this moment right here before having read something, having read something. And so state will here be nothing. The first state is nothing. Okay. And here let's create a function parse that takes the contents as a string, and let's put the loop right here. So and it's gonna be parser equal to conf parser new and parser dot parse. And so it takes self as mutable and returns probably a result. So yeah, and we're gonna deal with the configuration parsing here, right here. And we have to return. I'm returning a result because I think we will need to return a result someone. And I have to provide the contents, of course. Okay, and so now I want to match on self.states. Basically, I could be on tokens, alphabets, yeah. I can be on tokens, and I also be on nothing. I should first, how can I deal with this? I think the best thing to do is check if we are currently in like a state definition line. For example, this line is kinda special. It indicates that we are gonna read alphabets in the future. So I think the first thing we should do is do something like this. If line dot starts with this, no, I'm gonna do something else. I'm gonna implement the state, okay, with the next method. And basically, next takes a mutable reference to a state and a line that is str. And then it returns probably a bool. It returns a bool that said, yeah, it was a state definition line. And so here, if it finds that this is a line definition, it's going to change its own state itself. We don't need to handle this here. And it will return true to say, yeah, ignore this line. Don't consider this line as anything. I handle it. So we're gonna do something like this. If self.state.next, just continue, ignore. And I have to provide, of course, the line. And so here I want to check. I can do something like this. Line equal to line dot prefix, strip prefix with this. So it basically returns it can return known if the line is not starting with a hashtag. Otherwise, it will return the slice without the prefix that we provided here. And so if this succeeds, I want to do something like this. Match a line. Um, and it's gonna be something like this, alphabets, and gonna be states, alphabets, and the other one will be tokens. It's gonna return tokens. Okay. You disagree? Yeah, okay. And here I have to put true, surely. And here it's gonna be false. And basically, if I have something else, I want to throw an error. I want to throw an error because it means that you provided a state that does not exist. So it's going to be bail, invalid state definition line. Okay, and I want to do like change the states. So do something like this. Oh yeah, it's because it's a result. Let's wrap this condition under OK. Nice. Okay, it seems to work. I think it's what we want. Let's do a quick test, I think. Here I have to put a question mark. Okay. Let's print half a line token line, and let's run. Okay, and so it seems to work. Here we have the alphabets, and then then comes the tokens. So it's what we want. Okay, so let's do something like a self.read alph-decl, a read alphabet declaration, and let's provide the line. So this thing gonna be like so read alph-decl with the line that is str, and it's probably gonna return a result with nothing, because we just want to change the internal state of the parser. So we don't need to return anything. Okay, let's introduce alphabets. So the first thing I want, alphabet should be of the form a name, any name that does not already exist, then an equal symbol, and then like some quotes. So let's use a split once, a name and quotes. It's gonna be line that splits once with equal. Okay. So context invalid alphabets declaration. Okay. Um, yeah, it's because here I have to put a cool mark. And then what I want to do is check if the quotes are valid. So I want to ensure that quotes dot starts with this and also ends with this. That's basically what I want to check. Otherwise, it's invalid quotes for alphabet declaration. And let's put the name here because we can. And it's ensure. Nice. And I also want to check that that the length of the thing is superior than 1. Yeah. Yeah, clearly. And it's not a comma, it's a, oops, it's a end. Okay, nice. I need to trim. Yeah, of course I need to trim. So let's name quotes are gonna be name.trim quotes.trim. Okay, I need to trim before doing anything. And then I want to ensure that okay, I have to introduce the alphabets. So we are probably going to use a hash map. So it's going to be alphabets are going to be hash map that binding string with alphabets string. And so I have to use std collections. I'm going to use hash map and hash sets probably. And now we have to define what an alphabet is. It's not very hard. An alphabet will basically be something like this. We want to store the alphabet in the hash sets of I suppose character, because I said alphabet are just like a set of ASCII character. The only operation we're gonna do on the alphabet are gonna check if a letter is contained into it. So a hash set is perfect. Um, so yeah, we're gonna use this. So this is gonna be a new hash map, I suppose. And now I want to insert the alphabets. So it's gonna be self.alphabets. Yeah, I I have to put myself right here as mutable. So it's gonna be self.alphabets dot insert name dot toString, and it's gonna be alphabets with alphabet. Okay, and it's gonna be quotes one dot quotes dot len minus one. So we just remove the two quotes on the word, and then we want to get the cars, just the character, and collect it into a hash set. That's basically it. Yeah. So we are removing the quotes of the thing, then we get the cars, and then we collect it into a hash set. That's basically it. And if because I think yeah, insert returns an option with the possible preview, and so if this thing is sum, we want to bail, because it means you declared the same alphabet twice. So it's gonna be bail. You declared the alphabet name twice. Okay, nice. Okay, that's cool. That's cool. That's cool. Here I have to put a question mark. And let's print the parser just to check that everything is okay. The alphabet part was not really hard. You have to implement debug, of course. We can handle this. Debug. And yeah, here. And that's it. Okay, nice. And it's okay. So like here, we have alphabets here. Digits are those digits. They are not in the good order, but it's totally normal because it's a hash set. The notion of order has absolutely no sense. So it's what we want. And here we have the letters, and it's what we provided in the configuration side. So that's basically good. Moreover, what do we want to do if we catch a nothing right here? I think we want to bail, because we are not supposed to have a nothing at this point. It would mean that you are doing something like writing something here, and if you did not declare anything, I want to bail. So please declare the state before starting anything. And then we're gonna handle tokens. This one is gonna be more difficult. Yeah, it's gonna clearly be more difficult since we have to parse this expression. So yeah, we will have to think about it. Okay, so this is basically an onion, okay, and this is like a series of rules, you know. Like I want basically to declare a data structure that contains the rules itself. So the thing I'm probably gonna do, um, like you can see this as a single token followed by another one, and you can see this as a single token united with EOW, that is also a single token. And you can see this as a thing, yeah, I think it's gonna be like a recursive struct or a recursive enum. Yeah, it's like exactly what we want to do. Um, like um, you're gonna like do something like this. Enum rule. The first thing you can have is a letter. Like this is like atomic. This is basically atomic. It's like just a token name or an alphabet name. It's a name. It's atomic. You can't split it into multiple things. In a normal expression, atomic would be like imagine you have I don't know 1 plus 2. Atomic is 2, for example. You can't divide. This is also an expression, but you can divide it in two sub-expressions here. So this is atomic. And atomic gonna wrap a string. That is the name. Then you have a union. So union gonna be a vector of rule. Okay, and then you have a chain, and it's also gonna be a vector of rule. And the last one gonna be EOW. It's like a special token. And so because this thing can be represented only with this, you know. For instance, if we want to, it will be basically rule, and it will be, I suppose, an onion, okay, composed of um, a rule that is basically a chain. This rule, yeah, is basically a chain, and it's, I suppose, a rule, atomic digits with rule that is also atomic but a letter. That's basically our chain. Okay, right? Then, no, it's not this. This is into an union, I suppose. This is an union, yeah. So you're doing something like this. Okay, and then you have rule that is atomic. Atomic, and it's idon 2. That is idon 2. Okay, this is it. And then at the end of the day, you have like EOW. It like concludes the ultimate rule. That's basically it. That's how we're gonna represent the things. So yeah, let's do this. So the first thing we want to do in a read token declaration. So let's create a read token dec. It takes itself as a table and the content as a string. No, it's not content, it's line, sorry. And it's gonna be a str. It returns a result probably. We're gonna do basically the same as here because I want to split on the equal symbol. I don't need this, I don't need this, I need this. I could provide like a work function to do this, but we don't care. So we're not going to use name yet. Okay, so let's first call the function self.read token dec with a line. And so I think I can provide the question mark here. Yeah. And here I want to evaluate the thing. I want to evaluate the thing. So I want to have rule. It's gonna be rule.build or maybe try from. Try from it's not gonna be quotes. The expression and expression. Oops. Try from expression. And so um, we have to implement try from here. Okay, so let's do it. So implement a try from str for a rule. Oops, let's put it here. So type error gonna be anyhow error, okay, and try from. Can you help me please, Emacs? Thank you so much. And so it's gonna be a result like here. And so let's put it in to do. Okay. Let's so parse this thing. We're gonna use the very well-known methods to like pass through the postfig expressions to handle the expression. Yeah. So okay, let's declare a function like a to pf to postfix expression is gonna return a vector of string, okay, and gonna take the expression itself. And let's put it into do. It's a str, and let's declare evaluate pf that returns surely this self, and it takes pf tokens. It's basically this, and let's put it into do. So we can just do let pf equals to 2pf with expression, and then evaluate pf. Pf. Okay, that's basically it. Why are you complaining? Yeah. Nice. And 2pf, it returns a result, no? Let's return a result. Nice. Okay, you disagree because it's not it's a vector, of course. Okay, so let's do it. 2pf. 2pf, we're gonna iterate through the character for c in exp.cars. And let's put the example right here. Okay, so first we're gonna build an output, so let's name it output. I don't quite remember the algorithm, but as far as I know, you have to build a stack that's gonna and push, I think, the operators on the stack. Because basically the postfix expression is this. For example, in this case, we would return something like this. Letter plus, like digit, that's gonna replace this. The idea is to remove parentheses and to and to avoid dealing with parentheses. And so after you have this with a multiplied, and then you have a EOW with a plus. And basically what it does here, we have like to then um, evaluate this expression, we can just read this, read this, read this, and then we can adding these two, and then we have a result, res. So we multiply these two, we have a result, and then we're adding these two. And it does basically the same as this one, but it's easier to evaluate onward a string. So that's basically the idea. So as far as I remember, the idea is so here is just going to be the results, to instantiate a stack, operator stack. It's like it's logic, like you're going to just put the operators on it, above it. And so here, if we catch match C, if we catch an operator, so it's going to be a plus or multiplied, we're just going to push it someday on a stack. Operator stack dot push C. Okay. Otherwise, maybe we're going to find an opening parenthesis and we have to do something. Or maybe we're going to find an ending parenthesis and we're going to do something else. Otherwise, it means that we found like the character of one of the tokens. So we just need one more buffer, like a mut current token. It's going to be a string, and we just want to push it in the current token. That's basically it. Okay. So that's the idea. That's the idea. Um, okay. The first thing here we want to do is, I suppose, push the current token in the output. So we're gonna declare push token. It takes as mutable the token. Token is gonna be a mutable reference to a string, and we want to take also the output. It's gonna be a mutable reference to a vector of string. I think we're simply gonna do something like this: output dot push token dot drain up dot collect. Yeah. Like we are pushing into the output the content of the token, and we are like we are removing the ownership of the character buffer to put it into the output without dropping the string. It's like doing something like clearing the string and pushing the content at the same time in the outputs. It's basically what we are doing. And so the first thing we want to do here is to call push token with mute token, current token, and mute to outputs. That's basically the first thing we want to do. And then we want to check if let's sum C equal to operator stack dot pop. And if this one exists, it means that there is an operator on the stack. We want to do something like output dot push C dot toString. That basically this. So it has to be obviously mutable. I think it's enough. We probably, yeah, we have to check first if it is an opening. Yeah, I suppose. Let's keep it like this for now. It's a vector of character. Let's keep it like this for now. If we found an opening bracket, I think we have nothing to do. Yeah, we absolutely have nothing to do. Yeah, no, we anyway want to push the token. Okay. And we want to push this on the stack, I think. That's all. But the interesting thing comes when we are finding an ending parenthesis. So we want to first push the token. Okay, that's fine. Maybe we should do something to avoid repetition right here. Yeah, we'll see later. Mm, and then while let some c equal uh, to operator stack dot pop, um, we want to reach the corresponding opening parenthesis. So we want to first check if C is an opening parenthesis. If it is, we want to break. We want to break. And no, we want to continue. And we want basically to continue the main loop here. So it's going to be a main loop. We want to continue precisely this loop here because otherwise we're going to continue this one. So it's a continue main loop. Okay. Otherwise, we just want to push C, like the character, the operator that we had on the stack. And if we to string, I suppose. I suppose there is some mistake in this code, like I'm doing it quite fast and I don't quite remember how precisely it works, but I'm kinda sure that's it. And so here, if I arrive here, it means that I failed to reach an opening parenthesis, so I want to bail. I want to bail. Invalid parenthesis. Yeah, I want to bail. So here it means that I don't want to just simply pop because eventually the thing I popping is the opening parenthesis, and so we will have some issue. So I just want to check if there is something, and if C difference than opening parenthesis, I just want like I'm doing something, I'm pushing something only if there is something, and this thing is not an opening parenthesis. Uh, if C is different from this, I can push this. First, I want to pop dot unwrap. I can unwrap because I checked earlier that there was something exist on the. Okay, why are you complaining? What? Mm-hmm. Oh yeah, it's because I have to call to string, of course. And so I want to at the end I need to return OK outputs, I suppose. Okay, I think this thing works, but I'm not sure. So let's do a test and print the outputs. I think it works. It's like it's the very well-known postfix transformation algorithm. I'm just not quite sure of the. Let's do it for this one. Where are the yeah, I have to put a debug mark right here. No? Yeah, it's not output, it's outputs. And it failed. Oh yeah, it failed because it's not yet implemented. And what does it return? It's not what I want. I think it's not what I want. So it means that we did something wrong. It returns. Okay, so here I just want to. What is this? Uh, yeah, let's first, if C equal to a space, I want to continue. Okay. I don't know if it's gonna change anything, but I think yes. Okay, it didn't change anything. We had this. So digit letter is good. It's fine. It's what we want. Then we found idents and multiplied, and so we didn't get the EOW. Okay, interesting. What does it mean? Okay, the AEOW, we failed to get the AEOW because here we have to do a last push. So um, if um, token, current token, please, dot is empty. If this is not empty, I want to push token one last time. Um, oh, maybe I know why push. Okay, I think I know. I think I know. Push token with current token. And okay, so yeah, I precisely know what is going on. So let's do last push token, and in push token, uh, I wanna do something like this. If token dot is empty, if this is empty, I'm pushing into the output. Because here, for example, for instance, when I spot this first operator, for instance, I was pushing the empty token in the output, and it's not what we want. Okay, it's almost done, but it's not yet what we want because we are pushing EOW after the multiplication symbol. Um, but it's absolutely not normal. What the operation is? Ah, no, it is normal, but we are not pushing the plus. So while let's sum OP equal to operator stack, I think the stack is just simply not empty. Dot pop. We just want to like output dot push op dot to string. That's it. And I'm kind of sure I'm gonna do something like this. If op equal to this, it means that the parentheses are valid because we are not supposed to get an opening parenthesis without having it. It will mean that the number of opening parentheses and ending parentheses doesn't match. So let's bail in parentheses. Um, okay, it should work. Let's try. I did not print anything. Okay, I think it works. It works. It's exactly what we wanted. So nice. That's cool because it wasn't that easy. Uh, Perhaps there is some bug into the algorithm. I hope not, but maybe it is. My coffee is cold. Yeah. Okay, so that's good. Let's dive into this one. Let's dive into this one. Okay, so onwards this, we want to create the rule, the associated rule. How are we gonna do this? Um, so basically have this in input. We basically have this. Up. Yeah. We have this, and we want to output the rule. So the first thing, we will need a stack for this time the value, okay, the atomics. So it's gonna be a atomic stack because basically when I'm gonna read the first atomic, I want to push it on the stack to like save it and after recover it and wrapping it into a rule, but not yet. It's gonna be like a rule stack. It's gonna be a vec. The output. What is the output gonna be? I suppose we want to finish with something that we pop on the stack. That's basically it. Because for instance here, we are doing precisely this. We are pushing digits. Let's put the evaluation here in the stack here. We are pushing digit on the stack. Oops. Then we are pushing letter on the stack. Then we are popping digit and letter, and we are pushing DL. It's like the union of digit and letter on the stack. It's then we are pushing idont2 on the stack, and then we are popping these two and DLI2. It's the onion, like the rules for those three. It's a chain actually. And then we are pushing EOW, and we are pushing, popping these two, and it's like the final res, and we just want to pop at the end of the day the results. Okay. So what we wanna do is first have a token. No, yes, we can iterate through the tokens. So for token in tokens, and we wanna see if this is an operator. So match token with, so this one, this one. EOW gonna be a bit special, so yeah, we want to match with this one too. And otherwise, it's just an atomic. Okay. Why are you? Yeah, it's because I have to do this. Why? What the fuck? Ah, yeah. Okay. Uh, dot ensure unexpected error. This should never fail. So and it's okay. No, it's not ensure. It's context. Okay. No, this is this. What we wanna do? If we found something like this, we want to push an atomic on the stack. So rule stack, I'm gonna push atomic rule atomic atomic with token. Okay. EOW, it's gonna be the same, but it's not an atomic. It's simply a OW. Okay. Here comes the interesting part, because there is the operators. So for example, multiply gonna be let's R2 is gonna be rule stack dot pop dot context fail to pop R2. This should never happen, well, yet again. And R1 gonna be the second one, because R1 is basically before R2 on the stack, so we have to push first R2 and then R1 to pop first R2, because we're gonna push R1 in first and R2 in second. We're gonna pop R2 in first and R1 in second. So it's why we are doing these things in this order. And then we are going to do a rule stack dot push yeah, okay, it's quite interesting. Here I want to match R1, because basically imagine there is already imagine R1 is a chain, for example. It's basically this. Imagine R1 is a chain. Okay. Here I simply want to do R1 dots um, it's not that simple, I think. Yeah, it's not that simple. I think this should work. Okay, let's think about it later. We could do something like a rule stack dot push vec with the R1, R2. It should be a rule chain with this. Okay, it should work. And here it will be basically the same, but it will be an onion. And I think this works, but I'm not fully sure. Uh, let's print the results. Is rules, no, rule does not implement debug. Derive debug. Let's print the results. Println rule. Mm, yeah, it works. It clearly works. We got what we want. So we have an onion of digit or letter chained with the atomic ident 2. But now imagine I do this. It's gonna return me something which work. It basically works. What's here? But the thing is, I'm wrapping a chain in the chain. It's fine. It's totally fine. But it means that chain are just, yeah, but it works. I think it works. We can deal with it. Like here, instead of having a chain with 3 elements, we have 2 chain with the second chain with the first chain containing the second chain. But it's fine. But it means that this is not anymore a vector, but simply this. You know, I'm gonna have an error, yeah. Yeah, I have an error because they are not on the heap. Let's keep a vector, or maybe we can pass it as a box. I don't know. I don't know. Yeah, let's pass it as a box because here I have an infinite recursion data structure without passing on the heap. So yeah, I have to box the things, and so here I have to do box new this one. Okay. Uh, Probably I'm gonna do something easier. Let's remove this, remove this, remove this. Let's remove everywhere the stack pushing. And here too, I suppose. And let's do something like this. Rule equal to this. And let's do a rule stack that push a rule into a box. Okay, that's cool. Okay, so let's deal with this. I think it will be enough. And now I want to save the rule somewhere, probably here. So it's gonna be a hash map. Yeah. Uh, it's gonna be another hash map. And so here I have to add something. It's gonna be a box rule. Yes. And so here I just want to do this. It's gonna be basically this one. Nice. It's gonna be rules. You disagree? Yeah, because try from is gonna be box. Can I do this? Please, 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 please. I'm not sure. I hope I can. So this is not anymore a vector. This is not anymore a vector. Do you agree? Are you complaining? Why are you complaining? Yeah, it's because it's not true. Yeah, it's box. Yeah, nice. It works. And so the next thing I want to do is do a little ensure here because you can't declare an alphabet and a rule with the same name. So ensure that alphabet contains key name. I think it's just this. Not because you declared the name is already an alphabet. Already alphabet. And I have to do the same for the alphabets. Rules. The name is already a rule. Okay. Um, so yeah, I think it's good. I think it's good. Okay. So let's see grammar.conf. Let's reintroduce this. So we have this output. It seems to work, I think, I suppose. So here we have all the alphabets. Here we have the rules. So the first one is to build an ident. It's basically the chain of a letter and an ident2. And ident2 is an union of a chain that groups union atomic na and atomic ident2 and OW. Nice. Is this all for today? I suppose, but I'm not sure. We have two things to do. The first one is I want to check if all the names are valid. Like once we finalize the build of the parser, I want to check that all the names are valid. That's basically this. So to do this, I'm gonna probably yeah. Let me think. So I need to iterate through the rules. Okay. I need to iterate through the rules, and I have to find yeah. So I'm gonna implement the rules, and I have to look for something that does not that something that does not exist. Basically, fn contains valid atomic. We're gonna give it a hash set. So it's gonna have a hash name set that we're gonna build. Hash set of string. Okay. Um, and so let's put it in to do. It's gonna return a bool. Check. Let's create a check function that returns the results. Up. And so okay. Up. And so the thing we want to do is right here. After having parsed the entire thing, I want to build the hash, the name sets. It's gonna be basically self dot rules dot keys dot chain with self dot alphabets dot keys that collects into a hash set of string. dot cloned dot cloned. Yeah, it should work. I'm not sure. Yeah, it should work. We're gonna say it works. Let's print it just to be sure. Name set. We're just creating a hash set containing all the names. Yeah. Debug mark. Yeah, it works. Nice. Okay, and so for in self.rules.key, no, dot values, yeah, values, rule.check, what? What the fuck? Can you please recommend me this one? It's because I'm not taking self. Up, up, up. Check. What do we check? Contain valid atomic. With so the name sets. It's of course a reference. Okay, and so here we're gonna do this match self. Am I so atomic? Self atomic. Um, Contains if namesets dot contains not contains contents. I want to bail. In this case, I want to bail. So I'm gonna bail, for example, invalid name contents. Otherwise, if I have oops, something like a union or box or chain, I want to probably R1, R2 do something like oops, R1 dot check contain valid atomic with name sets, and same for R2. Okay, why are you complaining? It's because here we are returning nothing? I don't know. Why are you? Ah, what? Oh yeah, it's just because I have to provide here. Okay. So yeah, no, I can just avoid this. Yeah, yeah. Okay. And here, if I got something else, it means I have either EOW or atomic contained in a nameset. So I want to return OK. Okay, it should work. It should work. Let's test, but I think it works not hard here. Please, yeah, it works. It works, nice. And the last thing I would like to add before cutting the video right here is a last field in rule. Because basically here I would like to be able to provide this kind of thing. Let's imagine we want to build affectation rule. It will be something like this. In Rust, for example, let's, like the literal let's, followed by I don't, yeah, followed by something like comma or equal chain with equal chain with ident 2 ident 2 um, followed no ident 2 expression I suppose, but expression does not exist, but let's say ident for now, followed with a comma. Okay, but we can't provide literal right here, so we should add it. So let's do this. Um, let's do this. So it's when we are parsing this one. No, this one remain valid. It's when we are doing this. Um, so here is gonna be match if is there like a prefix, a string in Rust? Because there is prefix, there is suffix. Where is suffix? Yeah, strip. Give me all the strip method, please. Ah, trim and match. Trim and trim, trim, trim and matches. Trim matches, please. No. Return the string slice with all prefix and yeah. Okay, nice. That's what we want. Trim matches. So match trim matches um, of token. So it's going to be token dot trim matches with this. And it's going to be sum. So lit, and here we're going to return rule literal with the lit the toString. Otherwise, none. We're going to return atomic rule atomic lit. No, it's simply token. And so here I have to add literal with a string, but it's not the same as atomic. And so here, this thing is not returning us an option. No, it's not what I want. So, can you give me an example, please? Oh no, it's not what I want. Yeah, I really would like something that's a strip suffix and prefix at the same time. Okay, let's. Okay, it's okay. Match strip suffix. Okay. Match. I think there is another way to do this. I'm gonna check later, but it's okay. Probably here I'm gonna bail because it makes no sense to declare something that starts with with quotes but doesn't end with quotes. Invalid name. Rule literal lits. So it's some lits. Prefix. Okay, it's basically this. I think it works. Uh, so let's try, for example, to run the code and to print for sure. Let's print the entire parser. Okay, let's take a look. Where is the thing, the affectation? Where is the affectation? Affectation. So we have a chain with the let literal followed by the idents. Yeah. Then we have an union of this literal or the chain with equal idents and with this literal. So that's it. Yeah, I think we figured it out. So yeah. That's all for today. In the next video, I think I'm gonna do the parsing algorithm that takes an input a set of rules, like the results, this results. Yeah. Oh, what should I do here? I should do nothing. It's okay. So the thing that takes this data structure in inputs and that returns some sort of a tree or I don't know an iterator, so the token we'll see. But that's what we're gonna do in the next video. So yeah, so thank you for having watched the video if you're yet here, if you're still here, uh, and see you later.